Good morning, everyone. Welcome to the Quad Cities ASCE SAME conference. This is the structural track. I'd like to personally welcome you. My name's Nick Costello, and the other co-host is Alex Campbell. We'll be your moderators for the day. I'd like to ask everyone to keep muted during the presentations. And then at the end, we'll address questions. Please put them in the chat. In that regard, I'd like to introduce our first speaker, Mr. David Fenella. He's a Senior Director of Engineering at CRSI. He has 30 years of experience in the design of a wide variety of buildings and other structures. David has authored numerous technical publications and is a member of several ACI committees. He also serves as ASCE Committee 7. David is a fellow of ACI, ASCE, SEI, and in 2014, he was the recipient of an award for the American Concrete Institute for outstanding contributions to the reinforced concrete design practice. David is a licensed structural and professional engineer in Illinois and is a past board member and president of the Structural Engineers Association of Illinois. So I'll give a welcoming hand to David.
Thank you very much, Nick, and good morning, everyone. It's my pleasure to be back with you again this year. What I plan to do today in this presentation is to give a brief overview on how to determine reinforcing steel design and detailing requirements for diaphragms. What you'll see today is basically centered around building structures, but please keep in mind you can use this for any type of structure that has a diaphragm that will transfer lateral forces to vertical elements of some type of lateral force resisting system. So we're going to just show some real basic information on how to determine chord reinforcement, shear reinforcement, most importantly the shear transfer reinforcement, and collector reinforcement as well. So at the end of this, you'll have a general idea of, especially for cast in place steel reinforced structures. So that's our learning objectives for today. So we'll start out with looking at some of the basic references that this presentation is based on. We have a design guide for reinforced concrete diaphragms that we published not too long ago. Contains a lot of good information if you're not familiar with this type of structural element. Goes through how to determine the diaphragm thickness, how to get the diaphragm design forces based on ASCE 716 loads, how to model diaphragms. Now, generally, we have a computer program that will do this for us, and that's great. But it's also good to be able to check what's coming out of the computer program. And to also, if you have a simple structure, it may not be worth the time and effort to put it into the software. So for a lot of different reasons, it's good to have some simple models that you can rely on. And I've done a lot of comparison between the models and what you get out of, say, a structural software program like ETABS. And for simple structures, without a lot of different types of discontinuities and such, the numbers come out almost exactly the same. So you can rest assured these simple models give you good results. We're going to focus on Chapter 8 of this publication, how to determine and detail the required reinforcement. Now, within our time, we'll just obviously give a brief overview, but it'll give you more information if you're not familiar with this particular topic. And just to round things out, there are a number of different examples that illustrate a lot of different types of structures in that design guide. So that gives you an overview of that. You're going to see some references also today for the ACI building code, and that's the 2019 edition. So if you see a section number from ACI, it's coming from that particular document. Also, there are some references to ASCE 7, and that's the 2016 edition. As you probably know, there's a 2022 edition that came out. Not too many changes, for diaphragms, a few here and there, but basically it's more or less the same, especially for reinforced concrete structures. So given that introduction, let's go ahead and take a look at some of the different aspects. We're going to start out by looking at the reinforcement limits for any diaphragm. And if we're following the ACI code, you can find in sections 12.6.1 and 18.12.7.1 that if you have a one-way slab, a two-way slab that's acting as your diaphragm, the minimum reinforcement you have to have in there is for shrinkage and temperature, which is this 0.0018 times A sub G. A sub G being the gross area of the section you're looking at. Generally we'll do it per foot width, whatever the case may be. Very simply, generally speaking, you're going to get much more reinforcement than this unless it's a very lightly loaded structure. One very important aspect to keep in mind, and this is spelled out directly in ACI 12.6.3. Even if you're not following the 318 code, this is really mandatory. Any reinforcement that's required to resist in-plane forces has to be in addition to the reinforcement that's required for other load effects. So if I'm designing, say, a two-way slab and I have all the bars I need in the column and middle strips for flexure, those bars are not permitted to resist any in-plane forces due to, say, wind or earthquake effects. Any reinforcement for the wind or earthquake has to be in addition to that. The only exception is shrinkage and temperature reinforcement. The code does permit us to use that to resist some diaphragm in-plane forces. So, that could be very useful. Instead of adding additional reinforcement in certain cases, if you have shrinkage and temperature reinforcement, it is permitted to resist some in-plane forces due to wind or seismic. Okay, reinforcement detailing requirements. What we did in the design guide is summarize in one table, specifically table 8.1, what are all of the reinforcement detailing requirements for diaphragms and collectors based on seismic design category. So you see we can break it up into seismic design categories A through C and D through F. And for those of you who use ACI 318 all the time, I'm sure you'll agree that even after the reorganization, uh, the requirements are all over the place. So we don't want to miss anything that's important, and that's why what we did is summarize everything here in one table so that you're guaranteed not to miss an important detailing requirement for the diaphragms and collectors based on seismic design category. It's like I said, you've got to go through multiple chapters, as you can see very clearly here, and it's real easy to miss something. So we thought this table might be useful to get us in the right place and not miss anything important. All right, let's start looking at all the different types of reinforcement and how to calculate it. We'll start with chord reinforcement. And what I usually like to do is just to take a simple case. We have this plan building here with walls in both directions. We have this force V that's applied to this diaphragm. Could be from wind or earthquake, whatever the case may be. So in this direction of analysis, if we know that our concrete slab is rigid, which generally is going to be the case, except for very long, narrow types of structures, we can count on it as rigid, and we can distribute this force V based on the relative stiffnesses of these walls. So once we do that, we can find out what the reactions are in each wall, and we can model this as a beam. So this is a deep beam with 3 different supports, and knowing how that distributes across, it, for this particular case, turns out to be a trapezoidal type of load. We know R1, R2, R3, and what W1 and W2 are. We can easily draw the shear and moment diagrams. So why do we need this bending moment? Because if we're assuming that this is a deep beam, that bending moment is going to tell us how much chord reinforcement we need at either end perpendicular to the direction of analysis. So we look at this a little more in blowed up fashion. When we apply this shear force to the diaphragm here, this force I should say V, we'll have tension on one side, compression on the other. We're not worried too much about the compression force. Generally speaking, the concrete will be able to carry that without any reinforcement. It's these tension forces that we worry about. So we can calculate that very easily by taking the maximum moment we determined from our moment diagram and dividing it by the perpendicular distance between the tension and compression forces. Generally, we'll take that at about 95% of the length of the diaphragm in the direction of analysis. Now, as we know, this is a very simple approach, but like I had mentioned earlier, it's going to give you good results when the building is simple like this, compared to your computer output. So again, we're not too worried about the compression. It's the tension that we worry about. We calculate what that force is, and we set up our basic strength equation where that T sub U that we just calculated has to be less than or equal to the design strength and tension. Knowing that, the concrete can't take any tension by itself, we'll design all of the chord reinforcement to resist that tension force T sub U. So solving for that, very simply, whatever T sub U is divided by phi, which we can take as 0.9 because it's in direct tension, and then the specified yield strength of the reinforcement. So that gives us the chord reinforcement. That's illustrated here as these red lines. We need them at both ends, obviously, because V can act in either direction. Now, what happens when you have a fairly significant opening in your diaphragm? And generally speaking, if you have openings the sizes of elevators or stairways or any mechanical openings that are, say, typical in a building, they're not going to have a big impact on how the forces get transferred through the diaphragm. It's only when you have a fairly large opening like illustrated here that we have to look at additional reinforcement. These gray areas we typically define as subdiaphragms. So those subdiaphragms will also have tension and compression. So to find out how much chord reinforcement we need, we look at the overall one and calculate it just like we did in that previous slide. But we also have to look at these forces that happen at the center line of the opening as well as in the subdiaphragms. And the larger of the two forces is what's going to control and determine how much steel we need for chord reinforcement. So we'll start with TU, which we define at the center of the opening, so that we get from our moment diagram. And again, we can calculate that as MU divided by, say, 95% of the diaphragm length in the direction of analysis. Now, in addition to that, we're going to have this T sub U1 from the subdiaphragm. What we can do in that case, this is a moment diagram assuming that this subdiaphragm is fixed at both ends. So fixed at both ends, we can find from just our analysis what that moment is at that location, and that'll give us what the tension force is in that subdiaphragm. So we have TU open, we have TU1. The addition of those two will tell us how much steel we need there. We compare it to what we have from MU max and use the larger of the two. So this slide summarizes that for us. T sub U, based on the maximum moment in the diaphragm, and then the summation of what happens at the opening. The larger of these two forces is what we would use to determine what our chord reinforcement is in that particular case. So it's, again, a simple way to determine what that extra reinforcement has to be. Now, if you have a lot of discontinuities or it's not as simple as that, then we recommend, obviously use your computer program, and the finite elements will give you your best results. But something simple like this, again, it'll give you a good idea of how much steel you need in this particular case. So that chord reinforcement, again, because the force can act in either direction, that chord reinforcement is located around the opening as such. Now, let's talk about compression just a little bit. As I mentioned earlier, generally speaking, compression forces are going to be transferred into the concrete, and generally speaking, they're not going to cause any issues. For seismic design categories A through C, there are no requirements in ACI 318 to design these as if these were columns. Okay, so no special design or detailing requirements for those three seismic design categories. However, once we have seismic design categories D, E, or F, then we have to start providing some special transverse reinforcement within that chord to prevent it from buckling due to the compression forces. So those requirements are given here in section 1812.3.2, and those are summarized here for you in this particular case. So what you see here is a partial plan of a diaphragm. This darker black line here is the edge of the diaphragm, and there's an opening in the diaphragm here. So when this strut-like element is subjected to compression, what the code is telling us to do is that we have to provide some additional transverse reinforcement within that portion that goes along this diaphragm opening so that this part of that strut does not buckle in any way due to the compression force. And it kind of makes sense, right? For seismic design categories D and above, you can have some fairly significant compression forces. This just ensures that we're not going to have any issues due to those larger forces. Now, where do we place the chord reinforcement? Well, as we noted before, it's placed perpendicular to the lateral force. It's provided in addition to any other required reinforcement that you might have in a beam or a slab at that location. If we have a slab that doesn't have any perimeter beams, we'll usually locate this reinforcement right at the edges of the slab, and it's generally tied to either the top or bottom flexural reinforcement. However, if you do have perimeter beams in the slab, we like to locate the chord reinforcement outside of the cross section of the beam, sort of in this area here, because we don't want to introduce any additional tension or compression forces into that edge beam. So if this edge beam were not here, we would usually put the chord reinforcement somewhere out here, but we don't want to introduce any additional forces if you have a beam, and that's why we tend to put it just outside the cross section of that beam. Now, just to note, ACI 318 does allow you, instead of concentrating the reinforcement just at the edge of the diaphragm, it does allow you to uniformly distribute chord reinforcement within the gray areas that are shown in this particular figure. So you can do that. In some cases, it might be better because of maybe possibly congestion issues or whatever the case may be. You do have this option. The only thing is, if you have a situation like this, you want to make sure that this chord reinforcement is developed into the adjoining part of the slab, tension development length into that adjoining part of the slab. Okay, let's move on to shear reinforcement. So we have our chord reinforcement that takes care of the flexure part of our deep beam diaphragm, and we have shear reinforcement possibly that will take care of all of the other issues that we might have for that particular force. So we'll take our same building again, and we have our shear forces that are uniformly distributed along the lines where we have our lateral force resisting element. So this is just a repeat of what we saw before. We'll know what the forces are in each of those walls. We can easily draw the shear diagram and find that our maximum shear in this case occurs along this line where we have the longer of the three walls. So that's our maximum V. We can uniformly distribute that over the length of the diaphragm, which is L. So once we have VU max, we want to make sure that that's less than our design strength. And this is the equation for our design strength and shear, the first one here. We have ACV, which is the gross area of the diaphragm, minus any openings that might occur at that location. And then this first term is the shear force provided by the concrete. The second is the shear force resistance provided by any bars we have that are parallel to the direction of analysis. Now, generally speaking, because of their overall geometry, it's not uncommon for VU max to be less than or equal to just this part here due to the concrete. So usually what I'll do is I'll calculate V sub U and then check this part here, just the 2 lambda square root of F prime C. Lambda is that lightweight concrete factor. Usually that's going to work, and then I don't have to worry about providing any additional shear reinforcement. If we do have to provide additional shear reinforcement, generally what I'll do is combine it with the reinforcing bars we have for flexure in the direction of analysis. So if I needed, say, 0.3 square inches per foot, and then another 0.1 square inches per foot for shear, I'll combine the two together, 0.3 and 0.1, so 0.4 square inches per foot. Again, we're using the same bar, but we're increasing how much area it is, so we're not violating that rule in terms of not using the same reinforcement to do two things. Now comes the big part, the shear transfer reinforcement. How do we get the forces from the diaphragm into our lateral force resisting elements and any collectors that might be present in our particular case? So shear transfer reinforcement must be provided between the diaphragm and the vertical elements of the lateral force resisting system and the diaphragm and any collectors you may have in that direction of analysis. As we know, collectors are needed when our vertical element does not have the length as our diaphragm in the direction of analysis. So again, we're going to illustrate it very simply. This structural wall 2 traverses the entire length of the diaphragm in the direction of analysis, so we don't need any collectors there. But because this wall 1 does not traverse the entire length, we're going to need a collector on either side to, as the name suggests, take its portion of V sub Y, transfer it into the wall. How do we do that? Well, we can calculate what the shear flow is along those lines, take that shear force, divide it by the length, and get our shear flow, and then calculate it based on shear friction. So V sub U at any location divided by phi for shear. Mu is a coefficient of friction depending on what type of situation we have in terms of concrete that's cast later with a cold joint or not. And then F sub Y, of course, our yield strength of reinforcement. So what is this coefficient of friction? If the concrete is placed monolithically, like would be the case for the slab, the diaphragm, and this collector, then it's equal to 1.4 times this lambda, which is the lightweight aggregate factor that decreases the strength because of the lightweight concrete. When concrete is placed against hardened concrete that's free and such, and it has a full amplitude of 1/4 of an inch, you could take it as 1. This is generally when you have a cold joint. Another cold joint where it's not intentionally roughened, it's 0.6 times lambda. So this is the table from ACI 318 where you can find that coefficient of friction. So let's look at wall 1. If we want to find the shear transfer reinforcement between the diaphragm and the face of this wall, we take that shear force at that location we have determined from analysis, V1. We divide it by the length of the wall. That's the shear flow. Pardon me. That is the shear flow over the length of that wall. And then we divide it by phi, mu, and F sub Y. And that'll give us how much shear friction reinforcement we need that will be placed perpendicular to the wall. And that reinforcement will transfer its portion into the wall. Now, there's generally two different construction methods, especially for building structures. One method is where the wall is built up to the underside of the slab, then the slab is constructed, and then the wall above is constructed. So you're going to wind up with a cold joint above and below that slab. And we need to find out what the forces are in order to put the right numbers into that equation that I just showed you. So you could start here at this location, where in this particular case, we're going to assume the collector is the same width as the wall, and that'll become evident once we get into the next couple slides. So at that location, we don't have a cold joint because the slab is cast all itself. We know what the shear force is, and we use the appropriate mu to find out how much dowel reinforcement. That dowel bar is noted here. That will be developed into the wall and into the slab by L sub D, and those are our shear transfer bars that will transfer that shear force into the wall. Okay, so that's one location. What if the collector is wider than the wall? Sometimes we have to do this because, especially in higher seismic design categories, those forces in the collectors start to become very large. And they can't be transferred into the wall itself, especially if you have a very narrow wall and the slab is the only part that's able to transfer it. So you could transfer a part of it into the wall and a part of it into this effective width, which we generally take as the thickness of the wall plus the length of the wall divided by 2. In this case, this would be the equation to determine how much shear transfer reinforcement you need between the diaphragm and the wall. We'll come back to this a little bit later because of this eccentricity, we're going to need additional bars perpendicular to the direction of analysis. There's two other joints we need to look at. The joint here, this cold joint between the wall and the slab, this would be the appropriate equation to use to determine A sub S. And we also have the cold joint at the top, and this would be the appropriate A sub L, which is the entire shear transfer plus how much reinforcement you need into the wall for the strength of the wall itself. So you look at all of those different areas of steel, and obviously you would use the larger of those and provide that dowel bar at a certain spacing along the length of that wall. So that's construction method A. Construction method B is where the wall is cast before the slab is cast, and we come back and put these form savers in. Form saver is nothing more than we're going to take the slab reinforcement and basically screw it into this form saver. So there's threads at the end. There's all different types of proprietary systems, but your cold joint is here, and we would have to provide similar type of dowel bars. Now here we illustrate a hook bar and we illustrate a headed bar. You know, we don't usually recommend those using the different ones at the same time. It can be done, of course, without any issues, but this is basically for illustration purposes. Sometimes a headed bar, especially if you have congestion here, will eliminate some of that congestion. So once again, your cold joint occurs here. This is the equation that you would use to determine how much dowel reinforcement you would need at that location. And these dowel bars would also be have a form saver here, and they would be basically screwed in at that location and then developed into the wall with a hook. That's the case where the collector is the same width as the wall. We could have it also wider than the wall in this particular case as well. Okay, so now we have the shear transfer reinforcement between the diaphragm and the wall. What about between the diaphragm and any collectors? So over this area, we'll need possibly additional reinforcement as well. That reinforcement is the shear force at that location divided by the entire length of the diaphragm. And because the slab and the collector is generally cast at the same time, mu is 1.4 times lambda. Again, depending on the case, it more often than not, this amount of transfer reinforcement is very small. And whatever bars that you have for flexure will have enough capacity to be able to carry both the flexure and any transfer between the diaphragm and the collector. There could be cases where you need to beef those up a little bit, but generally speaking, you won't have to worry about that. Now, we're going to look at reinforcement due to eccentricity of collector forces. This is the case where we make the collector wider than the vertical element it's framing into. So we saw this basically in the last couple of slides. As I had mentioned, it's up to the designer to transfer as much or as little reinforcement, force, I should say, directly into the shear wall. Okay, that's represented by C sub D and T sub D, compression and tension. In terms of C sub V and T sub V, the amount we're going to transfer by shear, we could take this as whatever percentage we like. We could even make it 100% and not transfer anything directly into the wall. What you'll notice here, obviously, is that these forces, T sub V and C sub V, occur at an eccentricity with respect to the center of the wall. So you develop a bending moment because of that eccentricity, and that bending moment is going to need some reinforcing bars to resist it. That bending moment is determined from statics, okay, of this particular free body diagram that's shown here. So this is the effective width over which we're going to take that shear transfer from the diaphragm into the wall. So once we calculate M sub E from this equation, we can determine how much reinforcement we need at the ends of the wall to resist that moment. Okay, so if we go back again, this moment will be distributed over basically this length here, the length of the wall, but we'll take 95% of that length to get it to, say, the centroid of that reinforcement. So again, this is a tension force. So we take that moment, divide it by that moment arm, and then divide it by phi, which is 0.9, and F sub y. That'll tell us how much reinforcement we need perpendicular to resist that moment. Now, you don't need this reinforcement if you're transferring all of the diaphragm force directly into the wall. It's only when our collector is wider than the wall it's framing into. And finally, we'll look at collector reinforcement. Collector reinforcement is going to depend on, again, if you're going to take that collector as wide as or wider than the vertical element it's framing into. So we'll take that generic building that we had before. We'll look at the shear flow at this particular location. So again, from analysis, we'll know what V sub U is in that wall. We take V sub U divided by the length of the wall, L2 in this case, and that's the unit shear force across the wall, the length of the wall. We take that shear force V sub U, we distribute it over the length of the diaphragm. That gives us that shear flow here. So the net difference between the two is our net shear forces along the length. So between the end of the diaphragm and the beginning of the wall here, the shear flow is VU over L. Over the length of the wall, it's the difference between the two. So VU over L2 minus VU over L. And then at the latter part, it's nothing more than the same VU over L. To determine our collector axial forces, it's very simply done by taking the area under the net shear force diagram. So between the end of the diaphragm and the beginning of the wall, that's V sub U divided by L times this length L3. From the other end of the diaphragm to the beginning of the wall, it's nothing more than VU divided by L times its length L1. Okay, so your maximum collector force occurs at this location, and it could be tension or compression because the force obviously can go in either direction. So once we have that maximum collector force in tension, we can easily determine what the area of the collector reinforcement is. Again, knowing concrete's not going to resist the tension by itself, we have to do it with rebar. We'll take that T sub U, which is this maximum here, divided by 0.9 in Fy. That'll give us the area of collector reinforcement. This is for the case when the slab width is equal to the width of the wall. So how do we detail it? We'll calculate A as collector, and we'll put whatever bars we need, making sure that it's in the cross-sectional area of the wall that we're transferring the shear force into. For seismic design category A through C, this can usually be done without any issues. Once you get into the higher seismic design category, you might have issues here with congestion, and that's why you may want to take this out into an effective width and transfer it over a wider width to avoid that congestion. So here's the case again where the slab is greater than the width of the vertical element of the lateral force resisting system. We basically do it in the same way. We calculate our total T sub U, and it's going to depend on, again, how much we transfer directly into the wall and how much we transfer into the slab. But again, calculate your maximum value, divide by phi and F sub y. In this case, depending again how much you're transferring directly into the wall and how much we're transferring by shear, you'll calculate your total A sub S and then proportion it accordingly into the wall and into the remaining part of the effective slab width that we've assumed in this particular case. So that's the case when we have slabs acting as collectors. When we have beams that are acting as collectors, it's a little more complicated. These beams will generally support not only its own weight, but a fairly significant part of any floor load. So we're going to have flexure to worry about, shear, torsion, if it occurs at the edges of the building, in addition to our axial compression and tension forces due to the shear transfer into the diaphragm. So these are generally designed as, say, a beam column where we have bending and axial compression and tension. And the best way to see if things work or not is to get your beam size, put some reinforcement in, and then see where your loads in compression and tension and bending occur, and make sure all of those load points fall within your interaction diagram. That's generally the simplest way to check to see if these beams are adequate or not to carry the combined effects of gravity and axial compression and tension due to our lateral forces. Now, if we are in a building that's been assigned to seismic design category D, E, or F, there are some special detailing requirements that we have to provide once again. We want to make sure we have enough confinement. Say this is our collector beam in this case. So we have to have a certain amount of confinement when we're in seismic design category D through F. This figure 817 in the design guide summarizes all of the different transverse reinforcement requirements that need to be satisfied, depending on what the axial compressive stress is in that particular collector. It also tells us about spacing, what the between in the vertical direction as well as along the length of the beam as well. So all important stuff to keep in mind once we have a structure assigned to D, E, or F. Last two slides I'm going to show you are a summary. And what we decided to do for the two different construction methods is provide a graphic summary of what reinforcement is required and where are the equations in the design guide to calculate that reinforcement. So what you're seeing on this particular slide here are slabs that have the same width as the vertical elements of the lateral force resisting system. You can see on the partial plan what the different marks are. So mark 1 is for your chord reinforcement, 2 is for any shear reinforcement, 3 is the shear transfer between the diaphragm and in this case the wall and over what length it works for both at the face, the bottom, and the top surface that we discussed previously. Mark 4 are any shear transfer reinforcement bars between the diaphragm and collector. And like we said, generally speaking, the slab reinforcement is going to be good enough to do that without having to provide any additional reinforcement. And finally, these Mark 5, as you can see here, along the entire depth, those are our collector bars. So that illustrates on the partial plan all of the necessary reinforcements you need for the diaphragm due to transfer of the lateral force. You could look here at the different sections, method A and method B, and these indicate what those different bars are as well for all of the different cases. So this is when the slab is the same width as the vertical element. When it's wider than that, we show all of the necessary bars as well. You'll notice the only difference here now is that Mark 6 are those tension bars that we need because of the eccentricity that we've introduced by making the collector wider than the wall. Again, here's all the bars indicated on the plan and on the section for the two different methods. We thought it might be helpful to include something like this, so especially if you're not familiar doing these all the time, it shows you in one place where all the bars have to go and what type of bars you need without, inadvertently forgetting something. So what we saw here today was, a real general overview of what you need for these particular types of structures. There's a lot of other things, can go into detail. I think this gives a pretty good overview, I hope, of what is required in this case. So a couple last things I just wanted to share with you. Every year that we've attended, we'd like to give a discount to the participants. What you see on the slide here is our design guide on ACI 318. This particular publication comes in both print format and PDF. It's about just shy of 1,000 pages, and it covers everything that you might want to come across for building structures cast in place with non-pre-stressed reinforcement. So we offer a 15% discount for anybody that might be interested. You can go to our website and take advantage of that if you'd like. We've also introduced new design checklists, and these design checklists take what's in ACI 318 in our design guide and present in one place the essential information you need for design and detailing. And this goes back to what I was saying earlier. You design and detail according to ACI 318, you've got to go through a number of different chapters to make sure that you have all the requirements satisfied. These checklists ensure you will not miss anything. They're printed on this synthetic paper that's waterproof and tearproof, 3-hole punch so that you could put them in a notebook. And it's good to have, say, if you're checking someone else's work or if you are actually designing and detailing, to make sure that you don't miss any steps. So has a number of different advantages in these cases. Right now that's available are all the ones that are listed here. Within the next 2 weeks or so, we'll be introducing our seismic package and our foundation package as well. In case you're not aware, we do have a mobile app that you can download for free. It has a lot of good stuff there. Reinforcing bar dimensions. For those of you who might be familiar with our old bar cards that have been around forever, you can click on this part of the app and it gives you all that you need for dimensions detailing for reinforcing bars, standard hook details, bar markings, tie hook details, all this stuff. When you download, it's all there for free. If you're interested in calculating development lengths according to 31819 or our colleagues who design bridges, we have an Apple and an Android version that you can download. There's just a nominal charge for this. It's a premium feature of the app. If you download either one of these, you get for free our desktop app to calculate development lengths. So it's basically the same thing as our mobile app, but you can download it for your computer, and it's a little easier to use than, especially if you're at your desk. You could put it on your computer and find out what the development lengths are very easily: tension, compression, hook bars, headed bars, etc. And finally, if you're not aware, we have this Rebar U. Rebar U has, if you're looking for continuing education units, it has a wealth of different presentations that you can download and gain continuing education units for. You name it, it's there. So please visit this website. A lot of good information to either refresh yourself with or to look into something that you might have just occurred on your job that you may not have all of that familiarity with. So with that, Nick, I'm going to turn it back to you and see if we have any questions that the folks might have for us.
Thank you, David. Um, if anyone has any questions, please put them in the chat and we'll ask David.
There's a lot of information to absorb, so it's you guys could always email me if you think of something later. You have the contact information. Be happy to answer any questions if you have anything that you might think later on.
Here's one question. Is
Okay.
it generally considered best practice to detail the slab to wall for both method A and method B to allow the contractor full flexibility in construction?
Yeah, usually what I usually like to do is to talk with the contractor to see how they're going to do it. Uh, they'll generally have that information available, at the onset of the project, and then tell them, okay, this is the way we're going to detail it. And if you change it later, which they usually don't, be aware that this could be an extra service. So
Great. Well, it doesn't look like there's any more questions. Thank you, David. I appreciate your presentation.
well, thanks again for having us, Nick. We appreciate the opportunity to participate in your event once again this year.
Our next presentation doesn't start until 9:10, so we're on pause until then. Philip, I just made you presenter. Are you on the line? I can unmute you.
Yes, I'm on the line. I've shared my first slide.
Yeah, I can see it just fine. So, looks
Good.
great. Doing well this morning?
Yeah, how's it going up there?
That's going well. I got some snow. You know, the uh, sometimes it's sad to see, but that's okay.
Are you up in the Quad Cities area?
Yeah, Davenport. Yep.
Right.
Did you guys get snow as well?
Well, I live in Mayberry, Durham, North Carolina. So
Oh, okay.
our winter consists of about 4 days of overcast and temperature in the 20s or 30s. But still, the natives out here lose their minds, just absolutely lose their minds.
Yeah, I have a uncle out there as well, and he's basically like, "Don't go out because there's crazies out there." So,
I lived here about 4 years, a little over 4 years, and we had an actual measurable snowfall. Like 4 to 6 inches. Like actual snow. Within a month of when I moved here, and I used to live in Kansas City. I lived in the Midwest for 52 years. I was the only guy on my block that had a snow shovel.
that's a great accomplishment.
And, if I had to drive or go anywhere, I, I had the whole city to myself. It's great. My volume coming across good.
Yeah, I think it's a good volume. So, is your company based in Illinois then, but they have a office out there?
Yeah, our headquarters are there in Chicago, but we have my office out here, and then our diving division is in Paducah, Kentucky. And then we have a number of consultants that are kind of part time all the time in various places around the country.